Let's explore the powerful non-local keyword in Python. It shares similarities with the global keyword, but its behavior sets it completely apart. Imagine a function nested deep inside another function, and enclosing both is a master-outer function. This creates a clear hierarchy of scopes. When this super-outer function executes, it eventually returns our target nested functions. Let's see what happens next. Running this code gives us the value of our variable x. The magic happens with the non-local keyword. Notice how declaring x as non-local allows us to perfectly capture the value 10. You might wonder if standard scoping rules make the non-local keyword totally unnecessary here. Let's comment this out completely and rerun the script. We still perfectly retrieve the value 10. If we change it to 20, Python flawlessly picks up 20. So why do we even need non-local? It gives us the amazing ability to actually modify x. The value is currently 20, but to update it, we absolutely need non-local. Let's try assigning x to 30 right here in the nested scope. Running this confirms we successfully updated the value to 30. Let's add a print statement to highlight this incredible difference. Seeing is believing. Let me copy and paste this check directly into our nested function for a clear view. The print statement is ready to go. Now we can compare the before and after states. First, our initial x value is being printed, followed by our bold new declaration. We'll strategically move this print statement right below the non-local keyword for clarity. Let's run the code and see the magic. Awesome, we get 20 followed by 30. But what happens without the non-local keyword? Let's find out. Let's strip it away and carefully print the value of x right here. Boom! We immediately hit a frustrating error. It crashes, saying cannot access local variable x because it hasn't been assigned a value locally. This is super fascinating. We tried to print x, but Python simply blocked us. By commenting out the modification, Python happily grabs the correct outer value. But the instant you attempt to change it, it fails to locate that specific local variable. The ultimate fix is declaring it non-local. This tells Python to search the parent scope, and just like that, we get perfect output. It effortlessly taps into the scope above. Fantastic! Previously, I explained that non-local lets you access a variable from a higher level function. This shines with nested functions. Notice our super outer function nesting an outer function, which nests an inner function. That gives us 3 levels of indentation. We have one level right here, another for the outer, and our top super level. By using the non-local keyword, we can reach out, grab that variable, and instantly update its value. It looks like we are redeclaring x, but we are actually telling Python to use the existing x from the level above. We are keeping a direct link to it. It points directly back to it, but it doesn't stop at one level. If I comment this out, we get a syntax error. Python cannot find a local variable. The magic of non-local is that it can jump multiple levels up. There is no limit. Let's copy and paste this right up here. Just paste that in. Now our non-local command uses this higher x. It bypassed one level entirely. It reaches 2 or even 3 levels up. Running this works perfectly, outputting 20 and 30. The initial value was 20 from our super outer function. Then our inner function changed it to 30. Could we move this even further outside the functions? Can we place it up here at the very top? The answer is no. Python starts complaining. It tells us it cannot find variable x. The non-local keyword only works inside nested functions where it connects to an enclosing function. This outermost scope is the global scope. It is a completely different area. If we add the variable back into our function, the error vanishes. Let's change its value to 10. Now our global value is 20, and our outer function value is 10. That is exactly what prints out, 10, then 30. We are successfully updating the nested variable. This introduces Python closures. Python bundles all the variables that the inner function needs and packages them securely together. It keeps everything safe. Imagine it like a special box. Everything is grouped tightly inside. That is exactly what a closure is. That is the official technical term. Remember, this is not a global. You cannot use non-local to touch global variables. For that, we need the global keyword. We can simply type global instead of non-local. With non-local, our output is 10 and 20. But with global, the output becomes 20 and 30. Use nonlocal for variables embedded inside nested functions, and use global for variables in the global scope. In Python, functions can magically remember their values. Let's start with an outer function. Inside it, we have an inner function. This inner function will increase the value of x every single time it runs. Let's run this code. As you can clearly see, the value goes up by 1 each time we execute it. How does Python perfectly remember the value of this x variable? The secret lies in a magical feature called closures in Python. If we run the code without defining our variables properly, we hit a big error. Python complains it cannot find a local variable named x. This happens because x is undefined. If we set x equals 0 right up here and run the code again, it works perfectly. But notice something strange. The value is not increasing. It stays exactly the same. Every time the inner function runs, it resets the value to 0 and adds 1. We actually need this variable to sit completely outside the inner function, because the outer function keeps calling it over and over. The outer function gets stored right here. The inner function is returned, letting us call it through this exact variable. To powerfully preserve and remember our value, we use the nonlocal keyword with our variable name. This commands Python to hunt for the x variable in the outer scope. It searches up through the nested functions until it finds it. Once it finds it, Python uses it seamlessly. So x is safely outside the inner function. Imagine what happens when we execute this line to call our function. It only triggers the inner part of our code. This block executes, but the outer setup runs just once when first called. The outer function grabs the inner function and stores it. And brilliantly, it packages up our variable alongside it. This magical packaging is known as a Python closure. It's like boxing or enclosing the data. Python locks the environment inside a secure box and lets you safely execute the inner function. Even though x is not inside the inner function, it remains fully accessible. A strong reference is kept. Running the code now, watch the values of x constantly increasing. This is an incredibly useful technique to help Python functions remember past values. It's officially known as a closure in Python. It clicks when you see it in action, enclosing parts of your code and storing them safely. When called, only the inner function executes. The outer code doesn't rerun because it already ran once. It sets up, returns the inner function, and that is it. That variable is now perfectly available for use. I hope this fully clarifies how closures work. The outer setup runs just one time. Then the inner code runs repeatedly on each call. There we go. That is why our values increase. If you loved this video, please like and subscribe. Your support helps me create even more exciting Python tutorials for you. Here's another way Python functions can remember data. Yes, Python functions can actually remember data. Let's look at this code. We have a counter that increases by 1 every time we execute it. When we run this code, you will see that every time our counter function is called, it returns the count, which gets printed. We get 1, 2, and 3 exactly as expected, because it runs 3 times. Now, you might wonder about this part. Inside the function, it accesses its own attribute to keep track of the count. But where exactly is this count value coming from? This technique is known as accessing a function attribute. However, this specific attribute is actually declared outside. The function definition completely ends right here. That is it. But the actual attribute is assigned on this line, where we set count equal to 0. I can prove this by starting the count at 10. If we start at 10, the values jump to 11, 12, and 13. What happens behind the scenes? In other programming languages, you would normally expect something like this. Let's comment this line out and add a new variable right here, set to 10. Essentially, you're setting count to 10, adding 1, and returning that count. But the issue is that you keep resetting the same variable. When you call count here, you just return the local count. It resets every single time it runs, so you always get 10 plus 1 equals 11. The next time it executes, it does the exact same thing. 10 plus 1. It keeps overwriting your progress. We definitely do not want to overwrite it. We want the function to remember where it left off. So instead, we access an attribute here. But this attribute is not inside the function. It is set outside. Because if we set it inside, every single time this function runs, it will reset to the value of 10, so it has to be defined entirely outside. Python allows this because every single function is actually an object. You can attach custom attributes to it. So here you see 11, 12, and 13. Now, what if this attribute didn't exist? Let's comment this out and run the code. We get an attribute error. It tells us the object has no attribute named count. Since it is not defined inside the function, it must be created outside. Once it is created outside, your code runs perfectly. When Python reads this definition, it does not execute it immediately. Even when you run the script, Python is just creating the function, not actually running its internal code yet. Only when you call it does it execute. Let's comment this out again. It searches for an attribute called count and fails if it doesn't exist. But you can powerfully create it on the fly, dynamically assigning it right when you need it. So right here, I will define count, and at that exact moment, the property exists and is accessible. The function actually executes down here on these 3 lines. Only then does it hunt for the count attribute. Because we created it right before, it is fully available. But we cannot create it afterwards. Because of how Python flows, you cannot print the counter first, and then create the attribute later. That simply will not work. You can see it fails, because at the exact moment it executes the function, it asks, where is count? Since it is not defined above the call, it crashes. If I remove that bad call and create the attribute first, then execute the print, our code works flawlessly. I hope this clearly explains how Python functions can remember data using attributes. If you found this useful, please like, comment, subscribe, and follow. It helps the channel grow and reach more developers. I truly appreciate your support. Let's dive into the self variable in Python, especially when building classes. This trips up a lot of beginners. Think of this class as the perfect blueprint for a bank account. To keep things simple, every bank account needs an owner and a starting balance. The account must handle incoming deposits and allow customers to make withdrawals. Customers also need to check their current balance. When we create accounts for James and Sarah, we use that exact same bank account blueprint. It works just like a recipe. This recipe states we need an owner, a balance, and the ability to process deposits. It also needs methods for withdrawals and for displaying that balance. Let's see this in action for our users. When creating James's account, we set the owner to James with a balance of $1,000. For Sarah's account, the balance starts at $2,500. These specific bank accounts are now securely saved in memory. We need a way to track them. By storing them in these distinct variables, we can freely deposit and withdraw. Now, the self word you see isn't actually a strict keyword, it's just a variable. A huge distinction. When you create the bank account in your code, it automatically runs this init method. It acts just like any normal function. It just uses a special naming format so Python recognizes it. It's an essential requirement for classes. It must be named init, surrounded by double underscores. When you initialize a new bank account with the name James and a monetary value of $1,000, those instantly become the balance and the owner. So what is self? Think of it as the account saying, this is me. Technically, you can name it anything. For example, we could literally call it burger. To make this perfectly clear, Python lets you name this first variable whatever you like, but the strict industry standard is to always call it self. As you can see, the code still runs flawlessly. James has $1,500 and Sarah has $2,200. You can experiment with different variable names, but sticking to self makes your code readable for other developers. So why did the Python community choose self? Why not just use burger to make it highly memorable and fun? The word self carries deep semantic meaning in object-oriented programming. It represents the specific object being created at that exact moment. When James creates an account, that account is essentially saying, this is my account. This data belongs specifically to me. My owner is James, and my initial balance is $1,000. When Sarah decides she needs an account too, her account says, my name is Sarah, and my balance is $2,500. You'll quickly get comfortable using self as you write more classes. Python automatically passes the correct instance into that variable behind the scenes. It flawlessly remembers which data belongs to James and which distinct data belongs to Sarah. When you trigger the deposit or withdraw methods, the self argument is handled for you. You don't need to manually pass it in because Python injects the current instance straight into that self variable automatically. This keeps your method calls remarkably clean. To summarize, you can name this variable anything, but naming itself clarifies your intent for everyone. It tells other coders which exact account we're modifying. Whether it's Sarah's account or James's account, the object is simply referring to itself. I hope that clicks for you. By convention, always stick to the word self, even though it could technically be burger, chicken, or egg. Following best practices ensures your logic is robust, because you're isolating James's account perfectly. It focuses entirely on itself. You aren't accidentally tampering with Sarah's balance. It's all about me, me, me. I hope this deep dive helps clarify this crucial variable for you. Remember, it's a variable, not a keyword. Mastering the self variable changes everything. In a Python class, when you define a function, you have the incredible ability to call other functions from inside the class. Let us look at this amazing example. We have a customer class. The initialization method takes the customer's name, and the self variable simply refers to the object itself. So if you create a brand new customer called James, it gets stored right in this variable and gets passed automatically. Essentially, if you think about it, that variable gets passed right here as C1, giving you full access to James, the amazing customer safely stored in that variable. By convention, we always call it self, and then we assign the name to it. Now watch this greeting function. It also takes in self and then beautifully returns the word hello, a space, and the customer's name. But notice, this method is not being called directly from outside the class. It is actually called by the showMessage function. So when you run showMessage, you can see it does not take any extra parameters. This parameter is simply the object itself. It looks exactly like this. We have C1 here, and it connects directly to C1 over there. It is really that simple. Once again, it is called self by convention. Inside the message, we can call the awesome greeting method. Calling it right from within this function beautifully returns the text. It magically knows the name because of the self variable. It knows we want James, so it returns hello James and safely stores it right here. And then when it beautifully comes back, we append, thanks for visiting our store. Hello James, thanks for visiting our store. Running this incredible code gives us the output. Hello James, thanks for visiting our store. I hope this makes perfect sense. We have the ultimate power to call a class method from another method in Python, all by using the magical self variable. You cannot simply just call it directly. Remember, it is the self variable doing the heavy lifting. You cannot just type greeting, because Python will not know which object you mean. You must always write self.greeting. If you try to use the customer class and write customer.greeting, you will immediately get an error. This is because it strictly expects the self argument. That argument is missing because you're just using the class definition, not the actual amazing object that you just created. You must always pass itself. As I mentioned earlier, self comes directly from the object. When you trigger showMessage, it executes and passes the object variable right in. It is an incredibly powerful and smooth process, so it creates this fantastic linked effect. I'm just showing this for demonstration. Behind the scenes, Python automatically places the object into the self variable for us. I hope you found this exciting. Please like, comment, subscribe, and follow for more. If you have any questions, drop a comment below and I will answer you soon. Why define class properties inside the initialization method instead of just creating them on the fly as you need them? Let's look at this class called person. We will use the pass keyword here. This tells Python we aren't defining any contents for this class yet. We can leave it completely empty, but it is still a valid class. It is the absolute smallest example of a Python class you can write. Even so, we can instantly create two objects named P1 and P2. For object P1, we can dynamically set the name to James. We just created a brand new property on this specific object. It happens instantly on the fly, but watch what happens when we try to access the name on P2. That property only exists on P1, so P2 knows nothing about it. If we run this code, our first print statement successfully outputs James. But then it crashes. We get an error because P2 lacks that name property. To fix this, we would have to explicitly write p2.name equals Sarah. We skip that step. Once added, the code runs perfectly, but manual creation is tedious. That is where the initialization method shines. When we define properties directly inside the init method, they are automatically created for every object. both P1 and P2. Now, when we run this, the name attribute is instantly available for both. Another huge benefit is editor support. If we go back to our empty class, typing P2 dot gives us 0 autocomplete suggestions. The editor is totally blind. But if we use the proper initialized version and type P2 dot, watch this. The name property instantly pops up in the suggestion list. It is fully tracked and ready to use. This is the power of init. Every single object inherits that structure safely and reliably. When you add properties on the fly, only that specific object gets updated. Any other objects are left behind and will cause errors, forcing you into repetitive manual work. With init, we can even create Sarah without providing an initial name. The code still runs perfectly. We just get an empty string printed out because the property exists safely under the hood. No random crashes. If you enjoyed this tip, please like, subscribe, and keep coding. Let's see what the string method in a Python class does. The string method is great for representing objects whenever you use a print statement. For example, we have a class called person right here. This person class has two properties, name and age. When we create a person named Sarah with an age of 30 and try to print that object out, this is the default output we get. By default, Python just prints out the memory address of the object. That is not very useful. When you print something in Python, you want a user-friendly response. So in your class, right next to your init method, you can define a custom string representation. You just add the dunderstring method to your class. It must be named with double underscores on both sides of the word string. If you misspell it as string1, it will not work. It must be exactly right. Now, when you print the object, you get a beautifully formatted output saying, this is Sarah, who is 30 years old. Here we use self.name and self.age. These values are returned by our custom method. We use an f string. Inside the curly braces, we refer to the exact variables we want to output. The self.age variable will automatically convert to a string thanks to our f string. And by defining our return statement, we get the name, a comma, and then the age. We get the name, a comma, and the age of 30, with a space character right in between. Without implementing the dunderstring method in your class, you get that ugly default output when printing your objects. But for a polished and user-friendly experience, implementing this method will display your objects exactly how you and your users expect them to look. If you found this custom string method tip helpful for your code, please hit that like button, leave a comment, and subscribe for more awesome Python tutorials and programming knowledge. Let's master class inheritance in Python. Here is our person class. It features a name property and a greet method to welcome users. It basically says hello along with the person's name. Now we can expand on this. Let's create a specialized employee class. We define the employee class here. Pay close attention to this next part. We pass person into employee to set up our inheritance. Person is our parent class, and employee inherits directly from it. This grants employee all the parent's methods and properties. We use the pass keyword to leave the rest of the class empty. Next, we create an employee named James and call the greet method. It outputs, hello, I'm James. You might be wondering how this works. The employee class seems empty. It only contains the pass keyword. How does it successfully send the name James to the person class? If employee lacks its own initialize method, Python handles it. It automatically inherits the initialize method from the person class. Without a custom method, Python falls back to the parent class perfectly. The same rule applies to greet. It delegates the greet method up to the parent person class. Let's see what happens if we change this. I will define a custom initialize method inside employee. Then, I will comment out this line and add pass to keep the code running. Running it now throws an error. Employee object has no attribute name. This happens because we overwrote the parent's initialization. To fix this, we must explicitly call the parent's initialize method. We could assign the property directly inside employee. Our code would execute perfectly. But best practice is to pass values up. Let's explicitly call person.init. We locate the parent class. We find its initialize method. We pass in self and then the name. Now our inheritance works flawlessly. The employee initializer takes the name James from our object creation and sends it up to the parent person class initialize method, where it gets stored safely. Let's append the word parent to the name so we can trace the flow. This will clearly show what is happening. When we call the parent initialization, it updates the name value. That is how the suffix gets added. If we comment this out and use pass, watch what happens next. I will move this line down here. We no longer need the pass keyword. Let's run our updated code. Notice the difference. The name James is no longer sent to the parent class. But if we restore the call, it triggers the parent method perfectly. The parent suffix is added again. Without the parent call, it relies solely on the local employee method. It skips the parent setup entirely. That is the power of inheritance. You can quickly build an employee class from a base person class. By default, an empty child class inherits everything automatically. It seamlessly gains both the initialize and greet methods. But adding custom methods will overwrite the inherited ones. When you overwrite them, remember to call the parent's initialize manually.